Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. Till now what we have seen different aspects of momentum transfer and then heat transfer individually. Also we have seen when both momentum and heat transfer are combined, how to solve the problems. Then heat transfer combined with reaction, then how to solve the problems, those details we have seen. Now in this lecture we are going to discuss a few basics of mechanisms of mass transfer, the mass transfer by molecular transport as well as the bulk motion, and then we see a standard simple problem, diffusion through stagnant gas film, how to solve using the transport equation for the mass transfer that we are going to develop in this lecture. Okay. So, the basics of mass transfer, though all of them are known to you through your UG classes, UG transport phenomena classes. So, but however, it is essential to have a kind of recapitulation, because these equations, transport equations for the mass transfer whatever we are going to develop in today's lecture are going to be useful in the coming 2 weeks. Okay. We understand that mass transfer can occur by both molecular transport as well as the convective transport mechanism. So, whether not only mass transfer, if it is momentum or heat transfer, then also they occur both by molecular mechanism as well as the convective bulk motion mechanism as well, transport occurs. So, the same is true for the mass transfer also. So, we see a few basics of mass transfer by molecular transport mechanism, then mass transfer by convective transport mechanism. So, first molecular mass transport, that is well explained by the Fick's law of diffusion. So, that we see here what we do in order to understand the diffusion or in order to obtain the Fick's law of diffusion, what we consider? We consider a diffusion of helium in a thin fused silica horizontal plate of area S and thickness capital Y. Okay. So, that that experiment, demonstrative experiment that we are going to see here to understand how to get the Fick's law of diffusion, that we already know it. Okay. So, at t less than 0, that is before starting the experiment, what we have? We have a fused silica is there. So, the horizontal surfaces, both top and bottom horizontal surfaces of this fused silica plate are in contact with insoluble air, because the horizontal plate has been kept, which is made of fused silica, and then both the surfaces are in contact with the air, and then air is insoluble in this fused silica. So, that it is not going to interfere in the diffusion process of helium penetrating through this fused silica, because helium is soluble in silica, but air is not soluble. So, initially we have a silica, fused silica horizontal plate is there. So, and then helium substance is there. So, notations wise, helium we are giving A and then silica we are giving B, right. Thickness of this slab is capital Y. Axis coordinate system we are taking like this, horizontal is x axis and then vertical is y axis. So, y is equals to 0 is bottom plate, and then y is equals to capital Y is nothing but the top surface of the plate, right. So, at the top surface we are taking boundary condition that helium is not present. Okay. That is, the mass fraction of helium is 0 at the top surface. This pictorial representation is at t less than 0, where helium has not been introduced. So, insoluble air is present both bottom and top horizontal surfaces of this plate. Okay. So, this is the system that we are having. So, now what we do at t is equals to 0, we are going to introduce helium at the bottom, right, whose mass fraction we are taking W A is equals to W A naught, and this W A naught is nothing but the solubility of helium in fused silica. So, that is the maximum of helium that can penetrate or soluble in the fused silica at given temperature and pressure conditions, right. So, this air is replaced by the helium at t is equals to 0. So, then because of the molecular mechanism or molecular transport virtue, what will happen, this helium will penetrate into the surface gradually and then a kind of concentration profile would be developed. And then that concentration profile is function of both y and t for small t, right. So, then obviously what we have, we can have a kind of a profile something like this. So, this is W A function of y and t, right. But what happens when time increases gradually for a steady state or large t, this concentration profile whatever is there, it becomes independent of the time, and then this profile is linear. This profile is linear for large t, and then at largest for the such large values of time when steady state is established, steady state for the process of solubility of this component helium into the fused silica through the diffusion, that attains a linear profile. Okay, that attains a linear profile. So that flux whatever is there, that we can relate it to the concentration gradient of helium within this slab. So that is what is the basic experiment that we are going to have, demonstration experiment, and then from here we get the required so called equation for the flux, and then that flux we are going to relate to the concentration gradient. From there we get the Fick's law of diffusion, which we already know. Okay. So, in the system helium is species A and then silica is species B. Their mass fractions are WA and WB respectively. So, whatever we have discussed in the previous slide have been shown pictorially. So, at T is equals to 0, helium has been introduced at the bottom of the plate, fused silica horizon plate. So, the very first layer within the fused silica whatever is there, that very first layer, now helium is there at T is equals to 0, that concentration in terms of mass fraction we are writing WA naught. At y is equals to capital Y, the concentration of helium is 0, the concentration we are representing in terms of mass fractions for the time being, right. As the time progresses, this helium penetrates into the plate and then a concentration profile develops, which is a function of both space and time. Now, here we are taking only in y direction for the simplicity, one direction. Okay. So, that is for the small t we can have such kind of concentration profile, right. But as the time progresses, if you wait for the large time and then steady state is established, what we can find, this concentration profile is only function of y because it is steady state established, and then this profile is linear with the WA is equals to WA naught at the bottom surface, and then WA is equals to 0 at the top surface where y is equals to capital Y, right. So, because this thickness of this plate is capital Y, right. Area through which the penetration is taking place is S. Okay. So, all this information is provided here as a text to the students. So, finally, at steady state it is found that mass flow WAY of helium in positive y direction can be described to a very good approximation by WAY divided by S, this is nothing but the flux, and then it is proportional to the concentration gradient that is given by WA naught minus 0 by y. Y is 0 here because WA is equals to 0 at y is equals to capital Y. Okay. And then at y is equals to 0, WA is equals to WA naught. So, the concentration gradient is given by this expression, right. So, now here we have taken only in one direction for the simplicity. So, whatever y is there, that is the positive y direction, the direction in which the species is diffusing is shown, and then A is nothing but the component, which component is being diffused, that is shown here, right. So, that is mass flow rate of helium per unit area or mass flux is proportional to the mass fraction difference divided by the plate thickness, right. We are calling it as mass flux, not molar flux, because everything we have taken in mass units, including this WAR we have taken mass fractions, not the mole fractions. Okay. So, and then this rho is the density of the systems, both A and B system, right, and then proportionality factor whatever DAB is there, it is diffusivity of helium in silica, that is diffusivity of A in B. Now, the same equation if you write for a differential element within the slab. So, then how you can write? You can write minus rho DAB dWA by dy. Why this minus is coming? Because we know this mass transfer occurring from higher concentration region to the lower concentration region, and then as the y increases the concentration is decreasing. So, that is the reason negative concentration gradient is there. So, we have to have a minus here, right. So, whatever this WAY divided by the area through which diffusion is taking place S is nothing but the mass flux that we have already seen. So, this mass flux we can indicate by small j A y, right. So, these notations we are following as per the book Transport Phenomena by Bird, Stewart and Lightfoot, where small j's are indicating for the mass units, capital J's or capital N's that we are going to see, they are for the molar units. Okay. So, this equation is nothing but the 1D form of the Fick's first law, right. So, first index in this JAY indicate the species that is being diffused, that is component A here, and then Y second index, that is Y here, indicates the direction in which the diffusive transport taking place. Okay. Then it is valid for binary solid or binary liquid or gas solutions, provided that JAY is defined as mass flux relative to the mixture velocity, and then mixture velocity is nothing but given by the mass weighted average velocity of all the molecules A and B. VAY is nothing but the molecular velocities of component A, and then VBY is the molecular velocity of component B in y direction, and then these are not the individual velocities. So, let us say component A is moving in different in y direction in different locations, different values. So, all the molecules at different y locations, whatever the velocity of this molecule A is there, that has been averaged. Similarly, for the B also, right, and then these are the local velocities. So, these velocities are measured using pitot tube or Doppler velocimetry, etc. Right. So, V is the average in which VAY and then VBY are weighted according to mass fractions, that is the mass average velocity. Then in equation 3, species velocity VAY is not instantaneous molecular velocity of molecule A as mentioned, rather it is arithmetic average of velocities of all molecules of tiny volume element. Within the tiny element, whatever we are doing this analysis, whatever the A component moving in y direction, so all the velocities have been taken as a kind of consideration, and then their arithmetic average is reported as VAY. Same is true for VBY as well. So, mass flux, now if you wanted to report in terms of velocity difference as a gradient, then you can report JAY is equals to rho WA multiplied by VAY minus VY, right. So, this VAY minus VY is also known as the diffusion velocities, right, it is also known as the diffusion velocities. Similarly, for component B, we can write JBY is equals to rho WB multiplied by VBY minus VY, right. So, now if molecular weights of A and B are different from each other, then obviously what will happen, there will be locally shifting of center of mass in the direction of diffusion as two species are interdiffusing. Obviously, here in this case in the y direction, the center of mass of the species moves in y direction, and then because of that one there will be a kind of a flux will be developed, and then accordingly those fluxes JAY and JBY are defined, that is JAY and JBY are measured with respect to the motion of the center of mass. What is the motion of the center of the mass in this case? That is whatever the diffusion velocities are, difference between the velocities is there, that is mathematically represented, this motion of center of the mass. Okay. So, for binary system, if you add them together, that is JAY plus JBY. So, this is JAY, this is JBY, Now, we are taking rho common from both the components, from both the components, both the terms of the right hand side, then this is what we have. So, this W A V A y and then W B V B y is nothing but V. In the previous slide we have seen, that is the mass average velocity. From the remaining two components, if you take V y common, W A plus W B would be there, and then W A plus W B is nothing but 1, because these are the mass fractions, and then summation of the mass fraction should be 1. This is a binary system. So, only two components are there. So, now we have this is 0. So, that what does it mean? Sigma j alpha should be 0, and then alpha is the number of the components and all that. Okay. So, that means if you have a in the y direction, let us say if you are taking. So, that means if you have alpha number of components, if you obtain the flux of all the components in the y direction and then add them together, you are going to get 0. If you have only binary components, so then j a y plus j b y is equals to 0. The same thing we can write it as j a y is equals to minus j b y. So, in the vector form, now we are going to write the fixed first law. So, what we have seen, J A is equals to minus rho d A B and then concentration gradient. So, that concentration gradient in we are writing in the vector form. So, del W A we are writing. So, J A is equals to minus rho d A B del W A, right. So, similarly for B, if you write J B is equals to minus rho dBA del WB. Now, here component B is diffusing in A in this equation number 6, whereas equation number 5 A is diffusing in B. So, are they different or not, that we are going to see now, right. So, for a binary system, just now we have seen the summation of these two, that is summation of the mass flux should be 0. That is, when you add these two, what will happen? Or we take one flux is equals to the minus of the other flux, because binary system we are taking. So, J A is minus rho d A B del W A is equals to minus J B is nothing but plus rho d B A del W B, right. So, rho is the density of the system. So, that is going to be same. So, both of them are cancelled out, and then del W A is nothing but minus del W B, because it is a binary system only, right. So, that means DAB is equals to DBA. So, that means for binary system, whether DAB or DBA, it is only one diffusivity is required to define the diffusion of the system. Okay. Only thing that flux would be negative of flux of A would be the negative of the flux of B, that is it. But the diffusivity, only one diffusivity is required to define the diffusion in a binary system. Thus, for a binary system, only one diffusivity is required to describe the diffusion behavior, and then DAB is function of temperature, pressure and composition. So, what we have, this mass diffusivity DAB, earlier we have a thermal diffusivity alpha, that is K by rho Cp, and then before that we have the momentum diffusivity or kinematic viscosity nu is equals to mu by rho. So, all of them are having the units length square per time, right. So, they indicate the the molecular transport behavior in different processes, heat transfer, mass transfer and momentum transfer, like that. Okay. So, they have a similarity. So, what we do? We get dimensionless groups utilizing these diffusivity, then what we get? Prandtl number Cp mu by K, that is mu by alpha, and Schmidt number, that is nu by DAB, that is nothing but mu by rho DAB, and then Lewis number, that is alpha by DAB are possible, then that means K by rho Cp DAB, that is what Lewis number. So, now what we understand from these numbers, let us say if the transport is occurring, whether the momentum transport or heat transport or the mass transport, whatever it is occurring, if it is occurring only because of the molecular mechanism, which transport process is dominating? Momentum transfer is dominating, or mass transfer is dominating, or the heat transfer is dominating, that we can understand. and then accordingly we can simplify the problem if in a given problem all these transport processes are occurring simultaneously. That is the use of these dimensionless numbers in general. So, till now what we have seen? We have seen mass transport by the molecular transport mechanism. So, now what we are going to see? We are going to see the transport mass transfer by the convection, that is mass transport by the convection, and then same that mass transport whatever is there, that we also represent in terms of the molar units. So, that is mass and molar transport by the convection, that is what we are going to see now. That is simply when the mass transfer is taking place only by diffusion. So, what is the flux, what is the expression for the flux for component A and B if it is a binary system, that is what we have seen. So, but now the mass transfer is occurring by the bulk motion or convection. So, then what is the expression for this flux, that is what we need to understand, right. So, we know that rho alpha V or C alpha V, but we are going to derive them. However, before deriving these things we need to have a some understanding about the nomenclature. So, rho alpha is nothing but the mass concentration of species, that is mass of species alpha per unit volume of a solution, and then C alpha is nothing but the molar concentration of species alpha, that is nothing but number of moles of species alpha per unit volume of solution, and W alpha is nothing but rho alpha by rho, that is mass fraction of species alpha, and then X alpha is nothing but a mole fraction of species alpha, that is C alpha by C, and then rho is nothing but sigma rho alpha. Similarly, C is nothing but sigma C alpha. Here solution means one phase gaseous, liquid or solid mixture, whichever we are taking. Only thing that they have to be homogeneous, then only these equations are in general valid. Other relations amongst these C alpha, rho alpha etc. are provided here, which are all well known to us. Okay. M alpha is nothing but the molecular weight of species alpha here, whereas capital M is the molar mean molecular weight of solution. Okay. It is not the molecular weight of one component, but the molar mean molecular weight of the solution, whatever number of components are there. So, that should be considered. So, mass average and then molar average velocity we define now, because we know this we are discussing mass transfer by the convection. So, when it is convection, so then velocity would be there. So, then velocity, which velocity should we consider, mass average velocity or molar average velocity? Both of them can be utilized. So, individually we see what are they. So, in diffusive mixture various chemical species are moving at different velocities. Then if V alpha is the velocity of species alpha, which is nothing but average of all velocities of molecules of species alpha within a small volume, that we have seen. And then for a mixture of n species, the local mass average velocity V is nothing but sigma rho alpha V alpha by sigma rho alpha, and then sigma rho alpha we have seen it is nothing but rho, that is the density of the mixture. So, and then rho alpha by rho is nothing but W alpha, that is nothing but the mass fraction of species alpha. So, V is nothing but sigma W alpha V alpha. This is the mass average velocity, local mass average velocity, right. And then rho V is local rate at which mass passes through a unit cross section placed perpendicular to mass average velocity V. Okay. Now, it is local velocity, so that can be obtained by pitot tube or laser Doppler velocimetry. Similarly, molar or local molar average velocity if you wanted to define V star. So, again coming to the notation, wherever we have the star or we have capital letters like capital J, capital N etc., then those things should be related to the molar quantities. Okay. That is the notation that we are that is followed by the transport phenomena book by Burt, Stewart and Lightfoot. We are following the same thing. So, local molar average velocity V star is nothing but sigma C alpha V alpha divided by sigma C alpha, and then sigma C alpha is nothing but C, and then C alpha by C is nothing but X alpha. That means V star is nothing but sigma X alpha V alpha, right, and then CV would be local rate at which moles pass through a unit cross section placed perpendicular to molar velocity V star. So, in summary, V alpha is the velocity of species alpha with respect to fixed coordinates, and then V is mass average velocity, V star is molar average velocity, V alpha minus V is nothing but diffusion velocity of alpha with respect to V, whereas V alpha minus V star is nothing but diffusion velocity of alpha with respect to V star, local molar average velocity V star, and then these are V minus V star or V star minus V, whatever are there, they are in general known as the diffusion velocities. So, now what we are going to see now, molecular mass and molar fluxes. Molecular mass flux of alpha is a flow of mass alpha through an unit area per unit time. So, that means J alpha is equals to rho alpha multiplied by V alpha minus V, that we have already seen. Similarly, molecular molar flux of species A is number of moles of A flowing through unit area per unit time. So, then this capital J A star, right. So, this is in mass units basically, and this is in molar units, that is the difference. Capital J A star is equals to C A multiplied by V A minus V star, right. J capital J is wherever capital J or star are coming, then they are with respect to the molar units, right. Now, fix first law of diffusion if you write. So, in terms of mass units we have this thing, in terms of molar units we have this thing, right. Here in the mass units del W A we are having, in the molar units we are having del X A, right. In mass units, diffusion velocity is with respect to V, local mass average velocity. In molar units, diffusion velocity is nothing but with respect to V star, that is local molar average velocity. So, now expression for convective mass and molar fluxes. The flux is by convection, but we are going to write it in both mass and molar units. That is the reason it is convective mass flux and then convective molar flux. Mass may also be transported by the bulk motion of the fluid in addition to the transport by molecular motion, that we understand. Now, consider three mutually perpendicular planes of area ds at a point P, where fluid mass average velocity is V, and then pictorially is represented by this. The surface ds is there at this point P, we are taking the fluid mass average velocity V at all three planes. Basically, these planes are presented in one picture. The perpendicular plane is perpendicular to the x direction, another picture plane is perpendicular to the z direction, another picture plane is perpendicular to the y direction, like that only. That is a simple difference. So, volume rate of flow across the plane perpendicular to the surface element ds perpendicular to the x axis would be nothing but Vx ds, simple, because the mass average velocity at the point P is nothing but Vx, and then the area of the plane perpendicular to that x axis, x direction, is nothing but ds. So, now at this point, when it is perpendicular to the x axis, if you wanted to know the mass rate, then this one you have to multiply by rho alpha, that is you get rho alpha Vx ds. Corresponding things when perpendicular to y and z directions are there. So, then we have rho alpha Vy ds and then rho alpha Vz ds. Now, these three quantities, what we do? We multiply by their unit vectors in x, y, z directions, normal unit vectors, that is delta x, delta y, delta z, right. Then we divide by ds, then we add them together, then we get this is what, that is rho alpha delta x Vx plus rho alpha delta y Vy plus rho alpha delta z Vz. So, this we can write it as rho alpha V, and this is nothing but the mass flux because of the convection. So, it is the convective mass flux vector, generalized one, in kg per meter square second. Similarly, we can write using molar units and then molar average velocity V star, then we get C alpha delta x Vx star plus C alpha delta y Vy star plus C alpha delta z Vz star, which is nothing but C alpha V star, right. So, now what we have? We have the expression for the mass flux because of the convection as well as the molar flux because of the convection. That is the flux because of the convection whatever is there, that we got in terms of the mass units as well as in terms of the molar units. Previously the same thing we got when the mass transfer is only by diffusion, then flux because of the then flux in mass units and flux in molar units we have already seen. So, now these fluxes are in general added up. If you wanted to know the combined complete flux, then you have to add them together. So, then when you add them together, they are known as the combined flux. Combined mass flux is in small letters, that is N alpha is equals to J alpha plus rho alpha V. The same thing if you write in molar units, then capital letters, that is capital N alpha is equals to capital J alpha star plus C alpha, and then V star. V star is local molar average velocity, V is nothing but the local mass average velocity. So, notation for mass and molar fluxes are given here with respect to stationary axis, with respect to the mass average velocity V, with respect to the molar average velocity V star as given. So, if the velocity of species alpha is considered, so with respect to stationary axis it is V alpha, with respect to the mass average velocity it is nothing but V alpha minus V, with respect to the molar average velocity it is nothing but V alpha minus V star. So, mass flux of species alpha, since mass flux it is N alpha is equals to rho alpha V alpha. With respect to the mass average velocity, that is V alpha minus V terms. So, then J alpha is equals to rho alpha V alpha minus V, and then we are writing it mass flux. So, this last column is with respect to the molar average velocities, it is a hybrid flux. Hybrid flux because small j alpha is there and star is there. Small j stands for the mass units and then star stands for the molar units. So, both of them are involved here. So, that is the reason it is known as the hybrid flux. How it is both of them are involved? Because this V star is nothing but local molar average velocity, whereas the rho alpha is nothing but the mass concentration of the species alpha. Similarly, molar flux of species alpha, if you write with respect to stationary axis, N alpha, capital N alpha is equals to C alpha V alpha, and then with respect to the molar average velocity it is capital J alpha star is equals to C alpha V alpha minus V star. We are writing molar fluxes, but the middle column is with respect to the mass average velocities. So, that is the reason this is represented in red font. So, again it is hybrid flux because J alpha is nothing but capital J alpha is nothing but flux in molar units, but it is the diffusion velocity is whatever is there, that is given with respect to the mass average velocity V, not the molar average velocity V star. So, molar flux in terms of the diffusive mass velocities are reported. So, it is again the hybrid flux. Like that, other quantities we can evaluate. So, wherever this red font are there, so they indicate hybrid flux. Okay. Similarly, different equivalent forms of Fick's first law for binary diffusion is shown here. So, flux, mass flux, if it is represented, gradient is del W A, and then form of Fick's law is nothing but J A is equals to minus rho d A B del W A. Similarly, molar flux, then capital J A star, then concentration gradient is del X A, then form of the Fick's law is nothing but capital J A star is equals to minus C d A B del X A. Similarly, component A we can write here, the combined flux we can write here in mass units, molar units, as well as in terms of the diffusion velocities also we can write these expressions as given here. Okay. Now, we are going to write most conveniently used form of Fick's law in solving majority of the mass transfer problems in this course. So, with respect to the fixed space, what we have seen, mass flux is this one, in table 1 just now we have seen, and then molar flux is this one. Then if there exists motion of solution as well and in flux with respect to the average velocity of solution, then for species A, this is what we have seen, combined flux, right, in molar, in the in terms of the molar units, combined flux is the flux because of the diffusion in molar units, and then the flux because of the local molar average velocity is this one, both of them are added together, and then whereas J A star is nothing but this one, this also we know, and then we are taking only one direction for simplicity, that is in Z direction. Now, this equation we can use only, we know the V star, and then V star are the local molar average velocity that are in general not available. Bulk average velocities etc. are available for a given system, are measurable. For most of the system you cannot use always pitot tube or laser Doppler velocimetry to find out this average local average velocities, that is not possible. So, then we need to have an expression. So, what we do, let us say if you have a binary component, if you have a binary component, then if you have a NA and B, right, both of them you add together. So, then what we understand, sigma j alpha is 0 or sigma capital J alpha star is also 0, that is the summation of the flux because of the diffusion is there, that is 0 for all the components if you take the flux of all the components. So, then when you do these two, then what you get, C V star is nothing but sigma n alpha, because sigma C alpha V star is nothing but C V star, that also we have seen. So, this is what you get. So, sigma n alpha is nothing but C V star. From here V star you can have sigma n alpha by C. So, for the binary components, sigma n alpha is nothing but NAZ plus NBZ, we are taking only in the Z direction for simplicity. So, V star we have NAZ plus NBZ by C. So, this we can substitute here in place of V star, then we have NAZ is equals to, in place of capital J A star minus C DAB dou XA by dou Z plus CA by C NAZ plus NBZ, because this CA and then whatever remaining multiplied by this thing is there, that is nothing but your V star, this is nothing but V star. So, CA by C we can write as XA. So, this is the combined flux for a binary system, and this is the most convenient form of Fick's law that has been used for solving majority of the mass transfer problems associated with the diffusion, right, and bulk motion both. So, now same thing if you wanted to write in terms of the mass units. So, small Na is equals to small Ja plus rho A V, and then small Ja is nothing but minus rho DAB del dou WA by dou Z, we are taking here again only in the Z direction for simplicity. Now, here also if you have a binary system and then if you add the flux by diffusion for all component, that should be 0, that means sigma n alpha should be equals to sigma rho alpha V, that is this one, rho alpha, sigma rho alpha V is nothing but rho V, that we know, and then sigma n alpha is nothing but Na plus Nb for binary system. So, from here V you get Na plus Nb by rho, so that you can substitute here, so that this equation can be usable in usable form. So, that you get. So, here in place of a V you have Na plus Nb by rho. So, rho A by rho is nothing but Wa. So, this is the most convenient form of Fick's law of diffusion when there is a solution motion is also, bulk motion is also existing. So, this is the expression for the combined flux, right. So, now in these equations whether you write in molar units or mass units, generally one of the component flux, that is NBZ or NAZ, may be eliminated if we know the relation between NAZ and NBZ, okay, or one of them in general stagnant, I mean 0 if it is stagnant, one of the phase is stagnant, like that. So, that we see. So, now what if diffusion in reacting system? So, if there is a mass transfer plus there is a reaction also taking place. So, then reactions can be categorized in different ways, but now with respect to the problems that we are dealing with, that is the mass transfer combined with reaction. So, then reaction can be categorized as two types of reactions, homogeneous reactions and heterogeneous reaction. Homogeneous reaction takes place in the entire volume of the system, whereas the heterogeneous reaction in general takes on a specified location like surface of the catalyst, etc. Right. So, if it is homogeneous reaction, since the reaction is taking place in the entire volume, so that mathematical representation should come into the mass transfer equation accordingly, right. If it is taking only at the particular location, as surface of the catalyst, etc. So, then that information mathematically should come into the problem as a boundary condition, because it is occurring at a specified location. So, how to bring them into the picture, that is what we are going to see here. So, chemical reactions can be homogeneous or heterogeneous. In homogeneous reaction, the chemical change occur in the entire volume of the fluid. In heterogeneous reactions, the chemical change takes place in restricted regions such as catalyst surface. Mathematically as well, these reactions are represented differently, because one is taking place in the entire volume, another one is taking place only at specified locations. Okay. So, rate of production of chemical species by homogeneous reaction appears as a source term in differential equation obtained by the shell balance, that is also we are going to see. Whereas, the rate of production by heterogeneous reaction do not appear in differential equation, rather it appears in the boundary condition at the surface on which the reaction occurs. Okay. So, let us say for homogeneous reactions, rate of production we can represent by this expression, capital Ra is equals to Kn triple prime Ca power n, where Ra is the molar rate of production of A, Ca is concentration of A, n is the order of reaction. If first order reaction, then rate constant K1 triple prime has second inverse of units. Okay. For heterogeneous reactions, let us say flux is known at the surface, that is NaZ at surface is Kn double prime Ca power n at the surface. This reaction, whatever the Ca power n is there, that should also be found at the surface at which reaction is taking place, because it is a heterogeneous reaction, right. So, NaZ is the molar flux, K1 double prime or here Kn double prime is for first order reaction is given as centimeter per second. So, here double prime, here triple prime, they are just notations only. Triple prime indicates volume source and double prime indicates surface source. That is, triple prime is for the reaction taking place in the entire volume, double prime is for the reaction which is occurring only at specified surfaces. Now, shell balance and then boundary conditions in general that are useful to solve the mass transfer problems associated with the diffusion as well as the bulk motion and chemical reaction, that is what we are going to see. Because now we see the basics, and then after that we can take different types of problems associated as per the problem. Because now we see the balance equation writing boundary conditions in general for individual processes with and without reaction, so that when we solve the problems as per the problem, we can take the equations and then solve the problems without any difficulty. So, law of conservation of mass of species A in a binary system over the volume of the shell, if you wanted to write, rate of mass of A in minus rate of mass of A out plus rate of production of mass of A by homogeneous reaction. If it is homogeneous reaction, then it should come as a source term, that is what we are doing here, and then all that should be equals to 0, right. So, this is the balance equation. So, we are not going to do the differential equation derivation as we have done the momentum transfer equations or heat transfer equations, but every time we are going to follow this simple approach, because in the case of mass transfer, writing such kind of balance for a given specified problem is much easier. Okay. Similar balance can be written in terms of moles as well, and then chemical species A may enter or leave the system, but by both diffusion, convection, and then both of these are being included in combined flux capital Na, and then in addition species A may be produced or consumed by homogeneous chemical reactions, that also possible, right. After a balance is made on a shell of finite thickness, what we do? We apply differentiation principles and would get differential equation for mass flux or molar flux, right. Then substitute equations for mass flux or molar fluxes in terms of concentration gradient in differential equations to get an equation for the concentration. When we solve these problems, we can easily understand. Then integrating differential equations will give concentration profile which include integration constants, which can be obtained by the applying the boundary conditions. This very similar way like what we have done in momentum transfer or heat transfer kind of problems also. Okay. Now, what are the boundary conditions in general possible in the mass transfer problem? That is what we are going to see, because they are very much essential, right. So, and they are not conventional, they are not very generalized or conventional boundary conditions like no slip boundary conditions or constant temperature or constant flux, heat flux equations, etc. Those things we have seen. So, we have to be careful while applying the boundary conditions in mass transfer problems. One is the concentration at surface can be specified, that is the simplest boundary condition. Another one is the mass flux at a surface can be specified, that is NAZ may be some constant Na naught, something like that may be specified, or the ratio is known, NBZ by NAZ is known, then it is equivalent to the concentration gradient. Then if diffusion is occurring in a solid, it may happen that the surface substance, it may happen that at the surface substance A is lost to a surrounding stream according to this relation, Na naught is equals to Kc multiplied by Ca naught minus Cab, where Na naught is molar flux at the surface. It is a fixed value, it is not changing, right. It is not changing, it is not NaZ, it is Na naught, fixed one, right. Ca naught is the surface concentration, and then Cab is nothing but the bulk concentration or concentration in the bulk fluid stream. Kc is nothing but the mass transfer coefficient. Other boundary condition is the rate of reaction at the surface can be specified. That is, if A is disappears at a surface by first order chemical reaction, then Na naught is equals to K1 double prime Ca naught. This is associated with the heterogeneous reaction. So, that is rate of disappearance at surface is proportional to the surface concentration if it is first order chemical reaction. If it is second order chemical reaction, then power 2 would be there. Okay. So, here proportionality constant K1 double prime is the first order chemical reaction rate constant. Mostly we take first order reactions in the problems. So, those are the basics that we have seen, the basics of flux by diffusion, flux by convection, and then flux in mass units, flux in molar units. In either of the diffusion and bulk motion cases we have seen the combined fluxes, and then we have seen how to write the balance equations for the mass transfer, and then what are the boundary conditions required to solve the species concentration differential equations, etc. Those things we have seen. Now, what we do before going into the complicated problems of mass transfer combined with the heat transfer or reaction, etc., we take a simple diffusion through non-stagnant gas film problem, which is very well known and very basic problem in the mass transfer. So, diffusion through a stagnant gas film that we are considering here. Steady state diffusion of a component A through a stagnant gas film of component B with liquid vapor interface maintained at a fixed position is taken. So, what we have? We have a column in which we have a liquid A, and then interface of this liquid is located at Z is equals to Z1. And now, there is a gas stream above in which this liquid is diffusing, it is evaporating and then diffusing into that gas stream which is located above. So, obviously, this location Z is equals to Z1 decreases, but what we take for simplicity we take a fixed location, and then top of the column we are taking as Z is equals to Z2. The concentration at this location Z is equals to Z1 we are writing XA1, and then concentration at Z is equals to Z2 XA2. this XA2 is the fixed concentration we are maintaining in general in order to have a kind of a simple measurements, easy measurements. Now, in these between these two locations, if you wanted to find out the concentration profile of component A and or component B, how to do, that is what the problem. So, that is first concentration profile you have to find out, and then what is the flux, what is NAZ at Z is equals to Z1, that also we have to find out. That is the problem. So, let us say first we have to develop an expression for the flux. So, within this column, in diffusive column in which the diffusion is taking place, are only the diffusion region, not inside the liquid, within the diffusion region. So, this is the empty region whatever is there from Z1 is equals to Z2, in that region only diffusion is taking place between A and B. A is diffusing into B, B is non-diffusing stagnant gas film. Okay. So, now, within this region we take a film of thickness delta Z and then we write a balance. So, flux at Z is equals to Z, some Z location Z is NAZ, and then flux going out at location Z is equals to Z plus delta Z is Na at Z plus delta Z. So, this concentration XA versus Z if you represent, so then you can have a line curve something like this. The same thing XP versus Z also if you represent, you may have something curves like this. So, what are these expressions? Those things we are going to find out now, right. So, consider a system in which liquid A is evaporating into stagnant gas B. Assume that constant interface position is maintained at Z is equals to Z1. At liquid gas interface, the gas phase concentration of A expressed as mole fraction is XA1. This XA1 is taken to be the gas phase concentration of A, corresponds to equilibrium with the liquid at the interface, that is XA1 is the vapor pressure of A divided by the total pressure, provided that A and B form ideal gas mixture and that solubility of gas B in liquid is negligible. So, that means NBZ is 0. A stream of gas mixture AB of concentration XA2 flows steadily past the top of the tube to maintain the mole fraction of A at Z is equals to Z2 as XA2. Now, entire system is kept at constant temperature and pressure, and gases A and B are assumed to be ideal, right. So, there will be net flow of gas upward from gas liquid interface, and gas velocity at cylinder wall will be smaller than that in the center of the tube, because flow through pipes or tubes what we have seen, there is a velocity profile developed across the cross section even if the L by D is very large. We do not have a constant velocity in general. So, we have the maximum velocity at the center and then 0 velocity at the wall. That is what we have already seen in the momentum transfer part of the course, but what we are doing, we are taking it for simplicity, we are taking it as a constant velocity, right, and then that constant velocity we are calling Vz, right. So, now when this evaporating system attains steady state, there is net motion of A away from interface and the species B is stationary. So, NBZ is equals to 0. Then this combined mass flux units, this equation we have already taken. Here in this case what you do, NBZ you take 0 and then you take this NAZ, XA NAZ to the left hand side. When you take NAZ common, you have NAZ multiplied by 1 minus XA. So, in the subsequent step, that whatever 1 minus XA also if you bring it to the right hand side, then we have NAZ is equals to minus C DAB divided by 1 minus XA dXA by dZ. Now, this equation, actually what we need to find out, we have to find out XA versus Z. If you solve this equation, you can do it, you can get it, but we can solve this equation only we have this NAZ information, otherwise we cannot do it, right. So, that we can get by the balance. Now, steady state mass balance for Z delta Z thickness of column, we do S NAZ at Z minus S NAZ at Z plus delta Z is equals to 0. S is nothing but the area through which area of the column or the area of the thickness of the column through which diffusion is taking place, and then luckily and then in our system the area is not changing across the column height. Okay. So, we can take S constant value. So, S is the cross section area of column. Now, divide this equation by S delta Z and then apply the limiting condition delta Z tends to 0, then what you get? Minus d NAZ by dz is equals to 0, and then NAZ we already got minus C dAB by 1 minus XA dXA by dz. Right. Temperature pressures are maintained constant, and then it is mentioned that the system is obeying the ideal gas mixture. So, then what we can take? We can take this concentration C as constant, as well as dAB can also be taken as a constant. Then we have d by dz of 1 by 1 minus XA dXA by dz is equals to 0. First time integration you do 1 by 1 minus XA dXA by dz is equals to C1. Again integration if you do ln 1 minus XA by minus 1. So, that is minus ln 1 minus XA is equals to C1 Z plus C2 you get. Now, this C1 C2 if you know, then you can know the what is this XA profile as function of Z. So, we need two boundary conditions. So, we already have two boundary condition at Z is equals to Z1, XA is equals to XA1. So, this equation you get. Now, Z is equals to Z2, XA is equals to X2. So, then this equation you get. Now, if you subtract this equation, second equation from first equation, you get C1 is equals to 1 by Z1 minus Z2 ln 1 minus XA2 divided by 1 minus XA1. So, this if you substitute in the first equation here, you get C2 is equals to minus ln 1 minus XA1 minus Z1 by Z1 minus Z2 ln 1 minus XA2 by 1 minus XA1. So, now we have C1, C2. So, now this we can substitute in this equation to get the concentration profile like this. For simplicity what we do? Now, we take this term to the left hand side and then we combine these two ln terms in the right hand side. So, that we have minus ln 1 minus XA by 1 minus XA1 is equals to Z minus Z1 divided by Z1 minus Z2 ln 1 minus XA2 by 1 minus XA1. So, the same thing we can write like this equation. So, this is the concentration profile that we supposed to obtain between locations Z1 and Z2. Profile for gas B can be obtained by simply writing 1 minus XA is equals to XB, 1 minus XA1 is equals to XB1, 1 minus XA2 is nothing but XB2. Like that we can write in this equation, we can get concentration profile in terms of B. So, average values of concentration and fluxes in the region between Z1 and Z2 if you wanted to find out, we do in terms of B. So, now this equation if you write for B, what you can write XB divided by XB1 is equals to XB2 divided by XB1 whole power of Z minus Z1 divided by Z2 minus Z1. This is what we have, right. So, average of this one if you wanted to have, XB average by XB1 is equals to integral XB by XB1 dz divided by integral dz, and then XB by XB1 is nothing but XB2 by XB1 whole power xi dxi divided by integral of dxi, because now we are writing Z minus Z1 divided by Z2 minus Z1 as xi. Okay. So, that we have d xi is equals to dz divided by Z2 minus Z1. So, this Z2 minus Z1 would be coming both in the numerator and denominator of this expression. So, that they can be cancelled out. So, only dxi is remaining here. So, this you integrate, then so this equation up to this part is written again. So, this part if you integrate, you get XB2 by XB1 power xi divided by ln XB2 by XB1 and then whole divided by xi is there, but that xi limiting conditions 0 to 1. So, 1 minus 0 1 is there. So, that we are not writing, only numerator part we are writing. So, this is 1. The limits when you substitute, when xi is equals to 1. So, this XB2 by XB1 would be there. When xi is equals to 0. So, something power 0 is 1. So, minus 1 and then same is applied here also. Okay. So, that is XB average is nothing but XB2 minus XB1 divided by XB1, but there is a XB1 in the numerator in the left hand side. So, that we bring it to the right hand side. So, that whatever divided by XB1 is there, that one, and then this multiplied by XB1 is cancelled out. So, that we have only XB2 by X. So, that we have only XB2 minus XB1 divided by ln XB2 by XB1. So, that is XB ln, and then xi is nothing but this one, logarithmic mean of XB1 and XB2. So, in order to obtain the rate of mass transfer, we need to have the derivatives of the concentration profile. So, then what we get? We get dxb by dz. So, that would be easier. So, xa profile, this is what we have. The same thing in xb, if you write, this is what we have. In ln we are writing because we wanted to do the differentiation now. So, now if you get dxb by dz, if you wanted to do both sides, you have to differentiate with respect to z. So, what we have left hand side 1 by xb by xb1 multiplied by dxb by dz. So, 1 by xb by xb1 we are writing xb1 by xb and then multiplied by 1 by xb1 dxb by dz. This is what we have. So, this xb1 is cancelled out. The right hand side this ln xb2 by xb1 are constants. Also 1 by z2 minus z1 is also constant, and then this whatever z minus z1 is there. So, that is nothing but differentiation, we get differentiation of z minus z1 is nothing but 1. Okay. So, that means dxb by dz is equals to xb divided by z2 minus z1 ln xb2 by xb1, right. So, dxb by dz, we wanted to know the flux at z is equals to z1 is nothing, then that means in this equation wherever this xb is there, that xb should be replaced by the xb1, because at z is equals to z1, xb is equals to xb1, xa is equals to xa1. So, now rate of mass transfer at the interface, that is rate of evaporation at z is equals to z1, if you wanted to find out, that is NAZ is equals to, or NAZ at z is equals to z1 is equals to minus C dAB divided by 1 minus XA, but now we are evaluating it z is equals to z1. So, this XA should be replaced by the XA1 multiplied by dXA by dz, and then this minus dXA by dz is nothing but plus dXB by dz, because it is a binary system only where XA plus XB is equals to 1. So, that means dXA by dz plus dXB by dz is equals to 0, or dx or minus dXA by dz is equals to plus dXB by dz at z equals to z1 we are doing. So, and then just now we obtain this dXB by dz is nothing but xb1 ln xb2 by xb1. So, that xb1 from the dxb by dz, and then here whatever the 1 by xb1 is there cancelled out. So, then we have only C dAB divided by z2 minus z1 ln xb2 by xb1, this is what we have. So, now using xb average we can use in the above equation, because we already know what is xb ln. So, in place of ln xb2 by xb1 we can write it as we can write xb2 minus xb1 divided by xb ln. So, that is what we have written here. Now, this xb2 minus xb1, what we can write? Xa1 minus xa2. Why we have written in terms of xa1 minus xa2 in final form? Because the concentrations xa1 or and xa2 are given in the problem. Now, we wind up today's class with a simple example problem using the previous expression that we have taken, diffusion through non-stagnant gas film. So, diffusivity of gas pair O2 CCl4 is being determined by observing the steady state evaporation of CCl4 into a tube containing oxygen. distance between liquid level and top of the tube is 17.1 centimeter, that is Z2 minus Z1 is given. Total pressure on system is given, temperature is given, vapor pressure of CCl4 is given, cross section area of diffusion tube is given, that is 0.82 centimeter square. It is found that 0.0208 centimeter cube of CCl4 is evaporating. So, that means from here we can get what is NaZ at Z is equals to Z1. We have to do some simplifications in 10 hours period time after steady state has achieved. What is the diffusivity of the gas pair O2 CCl4? That is the problem. So, let us take a notation A for CCl4 and notation B for O2. Then molar flux of A is given, that is Na is given like 0.0208 centimeter cube per 10 hours. 10 hours is 3.6 into 10 power 4 seconds, and then flux we need in moles per meter square or gram moles per centimeter square second. So, then now here this centimeter cube, in centimeter cube the flux is given, flux is given in centimeter cube per time units per 10 hours. So, that we are converting into the required gram mole per centimeter square second. So, now this one we multiply by the density gram per cc, that is 1.59 for CCl4, right, that we can get, and then dividing by, then this quantity is numerator, what we get, we will be having in gram units. So, that we divide by molecular weight of CCl4, that is 154, and then this you get in gram mole per second, right, and then the area through which diffusion is taking place, that is also given. So, if you divide that quantity by the area, you get gram mole per centimeter square second. So, that is the flux is given, indirectly it is given. So, we convert it in required units. And then DAB from the equation that we have derived is nothing but Na at Z is equals to Z1 multiplied by Z2 minus Z1 divided by CLN XB2 divided by XB1. This is what we got, right. Na at Z is equals to Z1 is nothing but this quantity. Z2 minus Z1 is given 17.1 centimeter, something like that. C we can write as P by RT, Ln, and then the ideal behavior Robate. So, then XB2 we can write in terms of PB2 and then PB1. So, like this. So, XB2 by XB1 is nothing but PB2 by PB1. So, 7.26 into 10 power minus 9 is NaZ at Z is equals to Z1. Z2 minus Z1 is 17.1, R is 82.6, T is 0 degree centigrade 273 Kelvin, P is nothing but 755 mmHg. So, 755 by 760 multiplied by 2.303 LOG log I am taking, and then 755 divided by 722. So, that is coming out to be 0.0636 centimeter square per second. So, these tubes, whatever the geometry that we have taken, in general that is also used to measure the diffusivity in a very crude way. That is a very crude way of doing. Of course, it is a crude way because it is having several drawbacks, defects, and such as cooling of liquid by evaporation is not considered, concentration of non-volatile impurities at the interface is not considered, climbing of liquid up the walls of tube and curvature of meniscus etc. have not been considered. References for this lecture are provided here. Thank you.